All right. Okay, so this is week 4. So and we're starting with lecture 7. What I'm going to be doing today is I'm going to be showing you how we make the connection between statistical mechanics and thermodynamics. So we're mostly going to finish up what we were doing at the end of last lecture, where I introduced for you the Helmholtz free energy, and I showed you that this Helmholtz free energy, just defined in some arbitrary way as shown on the left-hand panel as U minus TS, turns out to actually be just the minus KT times the logarithm of the partition function. And today what we're going to do is I'm going to show you how we then compute other thermodynamic variables from the partition function. And I'm going to then show you how one talks about fluctuations in the canonical distribution. In other words, looking at fluctuation quantities such as energy fluctuations. We will see, in fact, that the reason that statistical mechanics works, meaning we can use the Boltzmann distribution, the canonical distribution, as well as the microcanonical distribution that we had previously. The reason we can do all those things and it not make any difference is because the distributions are very sharply peaked, and I'll prove that to you in the class. And then at the end, second part of the lecture, we will talk about the what's called the grand canonical distribution, where we now allow the numbers of particles to fluctuate as well as the energy. I will show you the interpretation of what that means physically, and so today you will finally learn what we mean when we talk about the reservoir in statistical mechanics. And that's what we will. That's probably as far as we'll get today. So let's then get started. So, and on the left-hand panel, I've given you the links, the section headings. So now what I want to start off with is so the next thing that we're going to do is we're going to connect the partition function to other thermodynamic variables. And there's nothing very profound in this. It's just really a question of recalling the definitions. So we started off with the energy. So we saw already that the thing that's called the internal energy in thermodynamics is just the expectation value of the energy. And if you remember how I calculated that was somewhere back here on the left page, where you just use the Boltzmann distribution, plug it in, differentiate the partition function, and with respect to beta, and then we got this result over here on the left-hand panel. So we're going to just simply rewrite that. So that tells us that U is the expectation of energy is kBT squared d by dt of the logarithm of the partition function. And since we know that the partition function is minus kt log z, that then says that the U is equal to minus t squared d by dt of F, the free energy, divided by temperature. And so that's how we can get the internal energy from the Helmholtz free energy. Now, if I want to know what is the entropy, so the last time we introduced the canonical entropy, which I wrote as S tilde. So the S tilde is just given by this definition over here. So I simply take the definition of the free energy and make S the subject. So that means that S is equal to simply U minus the free energy over temperature. And that means it's equal to minus T d by dt of F over T minus F over T, just plugging that in. And if you look at that, then you'll just do the differentiation. You'll see that that is nothing other than just dF by dt. And that's exactly what we expect from classical thermodynamics. So from now on, I'm going to drop the tilde. So just to give you a warning. So from now on, I will drop the tilde. So in other words, S tilde is now going to be written down as S like that. Okay, so that shows you how we start doing this. Now I want to introduce for you thermodynamic relations and thermodynamic identities. So let me, does somebody, you have a question, Jake?
Yeah, could you explain again when we use S to the S, we just.
So S was just the thing that we did when we were just counting quantum states in what we call the microcanonical distribution. And S tilde was the thing that we did when we introduced the canonical distribution, where we allowed the energy to fluctuate, but the temperature to stay constant. And what I've shown you is that those things behave in exactly the same way. So I'm now going to just drop the tilde because it's essentially the same thing as the entropy. And also in the homework, you are asked to show, it's just a one-line proof, that the definition of the canonical entropy is the same thing as the microcanonical entropy if you have a system of constant energy. So that's the difference. So did I answer your question?
Yes, where did you show that S to the S basically means S?
That's your homework. You're going to do that. You can ask in the discussion session later today if you're stuck, but it's very simple. All right. So now I want to look at thermodynamic identities, and so there's several goals in this section. So let me just go and outline them. So one of them is I'm going to derive for you the first law of thermodynamics. In differential form. I'm also going to answer a question that a lot of people get confused about, which is if I have the Helmholtz free energy or other variables like the enthalpy or the Gibbs free energy or any of these other things that people come up with in thermodynamics, the thing that is always very confusing for students to learn is what do these functions depend on? So the question that we're going to answer is what variables, what independent variables do thermodynamic functions. We call these thermodynamic functions, we call them potentials. So I'm going to just use that word. I'll put it in quotes. What independent variable do thermodynamic potentials depend on? And so an example of that might be the Helmholtz free energy. Another example might be the Gibbs free energy, which I'm going to introduce later. And then there's other variables as well that people who've done, say, physical chemistry probably will have encountered, like enthalpy and things like this. I'm not going to go into all of those things, but those are things that people who do thermodynamics definitely want to know, and I'll show you how one can understand that. And there's one of the other things that that I won't go into in the lectures, but there are, for those of you who have met thermodynamics and are puzzled by it and want to know answers to questions, there is for the discussion session, I've put in on the Canvas website an example sheet on what are known as Jacobians, the same Jacobians that you use to change variables in an integral. They can be used to simplify calculations, and that's the best way to do it. So I'm not going to do it in class. For those of you who are interested, you're welcome to work on that in the discussion session. Okay, so let's get started. So I'm going to so let's get started with the first law of thermodynamics. So what we're going to do is we're going to keep the number of particles fixed. And then the entropy depends on the internal energy, the volume of the system, the number of particles, but that now is said to be a constant. And so that means that it just depends on the internal energy and the volume. So if I were to look at what a derivative of ds looks like, that's going to look like ds by du at constant v du plus ds by dv at constant u dv. That's just a regular calculus. So what I would like to find out is I want to show what is the meaning of these derivatives here. So the question that we're going to now try to answer is, what is the meaning of these partial derivatives? And we sort of started with that when we were doing the isolated system, but I want to go into it now in a little bit more detail than we did then. So here is the logic. What I'm going to do is I'm going to consider making a change in the system, but keeping the entropy the entropy to be unchanged. So we're basically going to make sure that we're going to make what's called an adiabatic change on the system. So what we're going to do is we're going to consider a variation of u and v such that the entropy does not change. So if that's the case, then ds is going to equal 0. And that means that 0 then is equal to ds by du at constant v du plus ds by dv at constant u dv. Now what I'm going to do is these aren't arbitrary changes as they are in the top line. These are changes that keep the entropy constant. So I'm going to put a little subscript s on both of those variables. So that means then that I can now divide through by the change. So then 0 is equal to ds by du at constant v, du by dv at constant s, plus ds by dv at constant u. So that is just from calculus. Now, why do we do this? Well, we have an interpretation for one of these variables. Which one do we have an interpretation for? Well, it is this one. This one, we know that is what our definition is of temperature, or more precisely, 1 over temperature. So that's 1 over temperature. So therefore, what I can write down then is that that du by dv at constant s is equal to then, just making it the subject of this, minus ds by dv at constant u divided by ds by du at constant v. And then because that is ds by du at constant v is just 1 over temperature, that means it is minus t ds by dv at constant u. But let's go back to what this quantity is. So this quantity over here, du by dv at constant s, that tells you how does the energy of the system change when you change the volume, but you keep the entropy constant. So the change is an adiabatic change. That's exactly what we mean by pressure. I move a piston, I change the volume of the system, the energy changes, I'm not allowing any heat to come into the system or leave the system, so that's going to be the pressure. So this thing is the pressure in the system. And so what I've just derived for you, actually it's minus the pressure because I reduce the volume and the energy goes up. So it's minus the pressure. And so then what we've learned is that this tells us then that the pressure in the system is equal to T ds by dv at constant u. Okay, so this is an interesting equation. And you might say, well, I'd never have really known that to be true. I had to do all this messing around with partial derivatives in order to derive that. And it's true, there's nothing shaky about what I've done here, but it's not very intuitive. So when I advertised about Jacobians on the previous page, so this is something that if you want to know how to do all these mysterious thermodynamic calculations, like the one I just showed you, which seems lacking in motivation, but it ended up making an important prediction. It says the pressure is related to the change in entropy as you change the volume at constant energy times T. Okay, you didn't know that before, and I used that result earlier, but now I've proved it to you, but it's obscure, and Jacobians is the way that one can prove a whole slew of these very complicated identities in thermodynamics, which are known as Maxwell relations, and they're the thing that that people use a lot, and they're one of the reasons why thermodynamics has a bad name, because all the calculations and manipulations that one does with it seem to be lacking in motivation. It's just like, well, you do some calculus dirty trick and bang, you suddenly make this identification of something equals something else. And why is that technically important? It's important because you can measure certain things in the laboratory much more easier than you can other things. And these thermodynamic relations relate these quantities. So for example, suppose I want to know what is the heat capacity of a system at constant volume. Actually, that's not so easy to measure because I might change the temperature. I can measure, on the other hand, the heat capacity at constant pressure, and that might be easier for me to measure in the laboratory. And so, but the thing I actually am interested in is the heat capacity at constant volume. And so relating these different things by thermodynamic identities is what people do a lot, and this is this is an example of that. So now I've just derived this formula. Let me tell you what use it is, and then I'll take Andrew's question. So okay, so now we say so what? So now we go back to our relation up here. So what is then now that I've derived this, then I can go back to the equation for ds. And so now the ds is now 1 over t du plus p over t dv. That is a general relation now. And that means that t ds is equal to du plus p dv. And this is this equation is one that those of you who've done thermodynamics before will recognize. This says the work done is the change in the energy plus the work done in changing the volume of the system. So this actually is the first law of thermodynamics. Okay, and then so that's the first thing. Then I just want to make a comment that making a change in, say, e.g., a volume with ds is equal to 0 means that no heat is entering or leaving the system. And that is known as an adiabatic change or transformation. And what is an alternative to that? Well, you could make a change in e.g. the volume with the temperature not changing. And so that means that is an isothermal change. And so when you're looking at things varying in thermodynamics, as you see from the page on the left, we've got all these partial derivatives with certain variables held constant, and you really do have to keep track of all those things, and because they matter from the circumstances in which experiments are made, and so that's part of what makes thermodynamics difficult for students. We're not going to be spending a lot of time doing thermodynamics, but this is the way that one can derive these things from statistical mechanics. And if those of you who want to, you can go and work on the Jacobian worksheet and learn how to do all these things in a very simple way. Okay, so you had a question.
Yeah, just a quick question. What was your logic again for why partial U is expected to be with entropy held fixed? Why did you say that was minus the pressure?
Well, by definition. But if you go back to how we defined,
Okay.
right? I mean the work done. If I do pressure is force times distance. Sorry, pressure is force per unit area times the dV. So that's the force. So that's the force distance. So that's the work done. Okay, so that is what we call pressure minus pressure. All right. So let's now then ask the next question. So what are the implications for the free energy, the Helmholtz free energy? Usually if I say free energy, I could mean Gibbs free energy or Helmholtz free energy. Physicists, it's usually the Helmholtz free energy. So let's then say, let's take our free energy. That's defined as U minus TS. And now I know this first law of thermodynamics, which is the thing up here. By the way, this TdS is usually in thermodynamics is called dQ, which is the heat flow. So when you've done your undergraduate thermo course, that's what you called it, dQ. So let's now see what this means for the free energy. So the free energy, if I take the derivative of that and just use the laws of calculus, that is du minus T ds minus S dt. But I know that the first law of thermodynamics is true. So then I can write this as what? As minus P dV minus S dt, just plugging the first law in. And what that tells me is something interesting. This now then tells me that if I'm looking at the derivative of the free energy, it depends on dV and it depends on T. So that implies for me that the free energy is actually a function of the volume of the system and the temperature. So if you want to know it's a function, what does it depend on? The answer is it depends on the volume and the temperature. Doesn't depend on the pressure, doesn't depend on the entropy. Does indirectly, but those are the things that it depends on. And in particular, if I look at those derivatives, then I can read off following, well, minus P is equal to dF by dV at constant temperature, and S is equal to minus dF by dt at constant volume. And again, those are things that people worked out in classical thermodynamics. And so this is the way that we derive what functions depend on. So the bottom line is, to work out what functions depend on, you use the first law of thermodynamics, there's physics in that, and then you use calculus based on the definition of what that free energy is. So later we can do the same thing for the Gibbs free energy, but now we're going to move on to the next topic. And the next topic I want to talk about is the question of fluctuations, so thermal fluctuations. So the goal of this section is to answer the question. So far, we've talked about two different types of system. We've talked about isolated systems, and we've also talked about systems at constant temperature. And they're held at constant temperature because they're in contact with a reservoir. And those are two different situations, gave us in one case the microcanonical distribution, which is just S equals KB times log gamma. That's what we did at the beginning. And the canonical distribution, which was that P is 1 over Z, e to the minus EI over KBT, and I is what? State. This is the probability of being in a state. And in the microcanonical distribution, what is PI? One over gamma, exactly. So we've got these two different ways of calculating that I've shown you. And the question that we should now try to figure out is, so question, do these things give the same result? Do these different physical situations lead to the same physics? So perfectly good question. And the usual context that this is answered in is in the context of fluids. So remember, statistical mechanics was invented in the end of the 19th century, the first 10, 15 years of the 20th century. So what people wanted to know then was just, how do many body systems of gases, liquids, things like that, how do they work? That was the question of the day. And so they wanted to know, do these methods give you the same results? So the answer to this question is yes. But there's a caveat. And the caveat is as long as n goes to infinity. Which is certainly true in the system that most people are interested in. Okay, you want to understand the behavior of the gases in this room? Yes, there's 10 to the 23 particles in this room, something like that. So sure, it's a perfectly good limit. Today, when we're looking at, say, quantum simulations, or we're looking at nanotechnology, we're looking at biological systems, these assumptions actually aren't correct. There are differences between these different things, and one has to be a lot more careful about what is the environment that one is dealing with. So let's on the other hand, let's just stick with the classical behavior, and so let's try to see how they work. So what is the strategy that we're going to follow? So our strategy is going to be the following. So in one case, we have the isolated system. And that means that E is equal to a constant. In the other case, we have the system which is in contact with some huge reservoir, like that. And then this thing has T equals constant. And so in this particular case, over here, so this is a constant temperature. But the energy fluctuates. And so the question that we want to ask, the sharp question we want to ask, is how much does the energy fluctuate? So this is a prototype of the sort of questions that we ask in statistical mechanics of phase transitions, the normalization group, those of you who took my class last quarter, because when you go to a phase transition, these fluctuations actually become huge, and the physics is dominated by the fluctuations. But for most parts of the phase diagram, that's not the case. So we're going to compute how much does the energy fluctuate. So let me show you how we go about doing that. So the first thing is I'm going to define a quantity called the fluctuation. So this is the energy fluctuation squared. And how do I define that? Well, what I do is I take the system in a quantum state I measure how much its energy is different from the expectation value of the energy. If I were to take the average of that, I would by definition get 0. So, but if I square that, let's fix this typo. So if I square that, and then take the average of that, that will not be 0. And so that is a measure of how much the energy deviates from the mean value. So you can think of this as being, if I were to draw a graph of the energy of the system and the probability density of the energy, then what we're saying is the average value is going to be here. And then the behavior is going to be some sort of curve like that. And then what this delta E is something like this width over here. So that's the thing that we're going to calculate. So let's have a look at how we calculate it. So let's just make the comment. We look at EI minus this squared, because by definition, the expectation value of EI minus the expectation value of E, if we just took the first power, or what would that be? That would then be the expectation value of E, applying the expectation value to EI. And then what is the expectation value of the expectation value of E?
Expectation.
So again,
Expectation.
expectation value of E, yeah, the expected value, what is the expectation value of 3? It's 3, right? Okay, so this would then be the expectation value of E, which would be 0. So we look at the squared, because otherwise we'll just get something non-zero. Okay, so now let's calculate what delta E squared is. So if I expand this quantity, so I'm now going to expand oops, try again. I'm going to expand EI minus E squared like that. So the first term I'm going to get is the expectation value of E squared. So that's EI squared, so that's E squared, like that. Then what is the next term? So then I'm going to get plus the expectation value of E times its expectation value all squared. And then I'm going to get minus 2 times the expectation value of E times the expectation value of E, like that. And so then I'm going to end up with the expectation value of E squared minus the expectation value of E all squared. Okay, everybody see that? Okay, so now let's go and compute those things. So we know how to do it because we explained it last lecture. So if I want to compute the expectation value of E squared, so that is by definition 1 over Z, the sum over I, EI squared, e to the minus EI over KBT. And the expectation value of E is equal to 1 over Z, sum over I, EI, e to the minus EI over KBT. And this sum over I is a sum over what? Sum over states, exactly. The Pavlov dog response is working really well. So good. So then the other thing is, so now let's write these things down as differentials. So we know that this expectation value of E is just minus 1 over Z dz by d beta. We showed that last time. So now let's ask ourselves, well, what about the expectation value of E squared? So the expectation value of E squared is, what I've done is I've differentiated with respect to beta, 1 over kt, I've differentiated twice. So if I call this thing beta is 1 over kbt, then what I've done is I've differentiated twice with respect to beta. So therefore this thing is then just 1 over z d2z by d beta squared. And so therefore, now I've just put those two things together. So delta E squared is equal to 1 over z d2z by d beta squared minus 1 over z dz by d beta. Well, I have to square it because of the E squared. So this is squared like so. And now if you look at this thing, so can you all see that this thing is a perfect derivative? Look at it carefully and see if it's can you see that this is a perfect derivative? And if it is, what is it a perfect derivative of? So this is the sum of two terms, both of which are derivatives with respect to betas. And my claim is that this is equal to d by d beta of something. Let somebody else answer, please, Andrew. Okay. I'll give you another 30 seconds. So calculate. No pressure, no pressure. Ten seconds. Gabriel? Are you Gabriel?
Yeah,
You got it?
maybe
Give it a try. What do you get?
Z Ln Z.
It is what?
Z Ln Z.
You're saying
The derivative of Z Ln Z. It's Z times L. I think.
with respect to beta?
Yeah.
I don't think so. Well, actually, well, you're close. It's not quite. Anyone else? Yes, Josh?
Just because of the double derivative of bulk of Z.
No.
DZ d beta Ln Z.
Okay, I think you might be right. What are you saying? So delta E squared is what? D?
D is DZ beta Ln Z.
dz by d beta over what?
Nothing over times Ln Z. Wait. No, never mind, no.
I think you're all close. Let me write it down and you're all going to say, okay, that was obvious. Okay, I claim. See, look at this. This first term looks like d by d beta of 1 over z dz by d beta. Because if the d by d beta acts on the dz by d beta, I will get d2z by d beta squared times 1 over z, which is the first term. But now when the d by d beta acts on the 1 over z, I'm going to get minus 1 over z squared dz by d beta, and that's going to multiply the dz by d beta here. So actually that's it. It's just that. Everybody see that? We seem to have Pink Floyd setting up outside. I don't know why. Nice of them to do it, but this. So okay. So what is this thing inside here? You've seen that before. What is it? The answer is probably on the page somewhere. Yeah, it is. It's on the page. So what is that? Say it again. Somebody was saying it, yeah. It's U, right. Plus or minus?
Minus.
Right, it's minus dE by d beta, or if you like, minus du by d beta. That's exactly right. So then I can write this down as delta E squared then is equal to, changing it from beta, I can write it as k b t squared du by dt. Okay. All right. What is the change in energy with respect to temperature? How did we define that a couple of lectures ago? So, and this, by the way, is a constant volume. How do we, what is du by dt? The change in energy as I change the temperature. What is the name of the quantity that answers that question?
Minus the present.
No. Anyone? Anyone? No? That's chemical potential? No. So remember that there's a thing that if I ask how much energy do I need to supply to a system in order to change the temperature by
That's,
specific heat, right? So in fact, this is the heat capacity. So this is KB T squared times the heat capacity at constant volume. Okay, so, all right, now we're going to do a scaling argument. This is now interesting, okay? The heat capacity is going to be proportional to how big the system is. Remember, we had the specific heat, which was the heat capacity divided by the size of the system, which I complained is generically taken to be the mass of the system, but a physicist wouldn't say that. A physicist would say divided by n. So the heat capacity, we know, is going to be proportional to how big the system is. The amount of energy you need to supply to the system to raise it by one temperature is going to depend on how big the system is. So that's going to be proportional to n. We also know that the energy itself, the internal energy, or U, if you like, that is also an extensive variable that is also proportional to n. Okay? So now we've found a very surprising and interesting result. So if I now look at so I've calculated that delta E, but this is delta E squared up here, right? Delta E squared goes like that. So what we've calculated then is that if I take the square root of that, I get the magnitude of the energy fluctuation. And if I and that is going to go like n to the 1/2. If I divide that by the actual value of the average energy, that's now going to be a dimensionless quantity. That's going to go like n to the half over n, and that is going to go as n to the minus 1/2 as I take n goes to infinity. So as n goes to infinity, delta E over the mean value goes to 0. And it goes to 0 as 1 over the square root of n. So when we look at our probability distribution, well, let's see, I made a picture of it over here. So if I take this picture over here, and I stick it over here, so there it is. So there was our distribution. So what I've now just shown you is that this scales like n, this scales like the square root of n, and so basically when as n goes to infinity, what this distribution is going to look like is essentially this. Here's the average energy, and it's going to be a delta function of the average energy. And so therefore, what that tells you is that the canonical distribution is going to look like the microcanonical distribution in the thermodynamic limit. And so that's why we can use the most convenient distribution that we want in order to do the calculations that we want to do. Okay, any questions about that before I move on to the next topic? Andrew?
Civil lines that we made between uh, derivative of the expectation value of B with respect to beta and the mass and constant line. Is there a useful relationship linking the energy to the heat capacity constant pressure?
Yep, you can relate the heat capacity at constant pressure to the heat capacity at constant volume by using a Maxwell, what's called a Maxwell relation, the sort of arguments I was doing at the beginning of this lecture. And the best way to do those is by using Jacobians. And so if you want to learn how to do that, then take a look at the exercise sheet that I posted on the Canvas on Jacobians, which you can work on during the discussion session this afternoon. Okay, so let's now move on then to the grand canonical distribution. So what is our goal here? This is really kind of noisy. I apologize for this. I remember when the days when universities used to be places for quiet study and contemplation. But
We still have a discussion here and thing now, so we're gonna be just nuclear.
yeah, yes, that's a good point. We'll move the discussion session to the other room because it's too damn noisy up here. Right. Okay. Good point. Thanks. Chia. Right. Thanks for reminding. Okay. So now we're going to do is so up to now we started off with the microcanonical, and there we had constant energy, and we had constant number of particles. Then we did the canonical distribution. And so what we said is, well, constant energy, we don't really need that. So we'll drop the constant energy. And then the constant energy, we'll throw that away. And if we threw that away, that then meant that we'd have constant temperature. So that's what we did. So now we're going to take this process even further. We're now going to do we're going to do what's called the grand canonical. And we're going to say, well, constant N, don't need that. Constant E, don't need that either. So we're going to cross out both of those things. So this one, we know that tells us that we have constant temperature if we take that off. And this thing gives us something else being constant. And we're going to find out what that is. So that's the first thing we're going to do, is we're going to see what happens as we relax these constraints even further. And we're going to say we're going to allow the particle number to fluctuate. So the bottom line is a fluctuating energy and particle number. So you might say, okay, well, that sounds really, really weird, because it was hard enough for us to believe that you can do the canonical distribution at constant temperature, and we had to do some work to make sure that it really gave the same result as the microcanonical, the constant energy setup that we were used to. Now we're going to make the particles numbers fluctuate as well. What the heck does that mean? How can that possibly happen? There's not people going around abducting atoms from your physical system or things like that. So the first thing is the first question that you're going to ask is, how does this make any physical sense? And my answer to that is it makes a lot more physical sense than the canonical distribution. So the answer is it makes a lot of physical sense. More than the canonical distribution. And why is that? Why? Well, the reason is that the energy is carried by the particles. We're making the energy fluctuate, but not the particle number, is kind of truly weird and unphysical, but having both of them fluctuate isn't so bad. So let's talk, let me now give you the big reveal. Let me show you what it really is all about. Here's what statistical mechanics is all about. So here is our isolated system that we've been talking about since week 1, and now we're into the middle of week 4. So that is our physical system. And now what I'm going to tell you is that it's not the physical system that we care about. Okay, so I'm going to draw inside of that another little box like this, and I'm going to claim that I have my particles are flying around inside the box like this. I don't know, however, like that. So that's what our physical system looks like. This thing over here is an isolated system. This thing over here that is the system that we apply statistical mechanics to. In other words, the system that I called capital S last week when we were doing the definition of the derivation of the Boltzmann distribution, and then the thing that is on the outside of this, all of this stuff. What is that called? What is that? The universe? No. The reservoir. This is the reservoir. So actually, so it's not like there's this mythical reservoir and it's something that, people talk about. We make ensembles, we make copies of systems, blah, 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 all the things that you read about in textbooks. Actually, what we've done is we've taken a big isolated system, we're taking the limit and it goes to infinity, we're making a big system, and then we've said, we're going to just look at this bit over here. So we're going to draw these dotted lines in the middle. That's going to define our subsystem. Particles are flying in and flying out of it. They fly in and they fly out. They take energy with them. So the particle number fluctuates and the energy fluctuates. And the whole thing is in thermal equilibrium with the rest of the system, which is the reservoir, because that's the stuff that's not in the system that we care about. And that is an isolated system. So actually, this physical picture of what it is that we're actually calculating the properties of, this is what we're really doing. It's much, much more physical than anything else. And so this setup, this grand canonical distribution, this setup naturally has energy and number fluctuations in the subsystem S that we calculate. So that's what it all means. And the point is, we will see that the fluctuations in particle number go to 0, just like the fluctuations in energy over energy go to 0. So we'll see that. And then the thing that holds the system constant, so the variable that is constant for the particle number fluctuations is the chemical potential. So that's the physical picture. That's the setup. So now let's do the calculation. So we're going to, so the first step of the calculation is I'm going to introduce the Gibbs free energy. So my Gibbs free energy, I'm just going to define it like this. Why do I define it like this? Well, because clever people in the 19th century who invented thermodynamics realized that this is a really useful variable, and we're going to see. So we're going to see what it means. So we're going to do that, and again, U we know has a statistical mechanical interpretation as the expectation value of energy. Now, if I write down what is du, then that is going to be defined like this. Du is TdS minus PdV. That was the first law of thermodynamics that we did before, like half an hour ago. The first law of thermodynamics when there were no number fluctuations. So when there are number fluctuations, then we're going to add another term to this, which we'll write as mu dn, and that's going to define the chemical potential. Okay. So now let's compute. Okay, once I've got that, so then let's ask the next question. What does G depend on? So we do the same thing as we did before. We say, well, if I have G is defined like that, then dG is du plus P dV plus V dP minus T ds minus S dt. That's from calculus. And then putting in the first law of thermodynamics, that then is equal to mu dn plus V dP minus S dt. And so that then tells me that the Gibbs free energy is a function of N, T, and P, because its derivative is a function of N, dP, and dt. So now we know that, and we can calculate what those derivatives are. So the coefficients are then identified as, you can see that mu is equal to dG by dN at constant temperature and pressure. We can see that minus S is dG by dt at constant N and P, and V is equal to dG by dP at constant N and T. So that's what those variables are. And if you've done physical chemistry, you might get very excited about that. But if you haven't, then you probably will just say, okay, so what? And that's basically my reaction. But now I want to show you there's a very important simplification here. So that's true, but now there is an important simplification. And that comes from scaling. So when I talk about the word scaling, what I mean, or what I always mean by that, is I'm going to look at how the variables depend on another quantity as that quantity goes to 0 or infinity. That's what I mean by scaling. And in this particular case, we're always talking about the thermodynamic limit where the number of particles is going to infinity. So that's the limit that we are interested in. So an important simplification from scaling, and what that really means in the language of classical thermodynamics, i.e. the difference between extensive and intensive variables. So when you did thermo, as it were, as it's always called, when you did your undergraduate course on thermodynamics, statistical thermodynamics, the names of the courses are different, what do you mean by extensive? Is a variable that is extensive that means that the variable is proportional to n to 1 power, and an intensive variable means that it is independent of n, which means it scales as n to the power 0. In other words, it's a constant. So what variables depend on the size of the system and which ones don't? So let's give a few quick examples. So extensive variables. Well, there's the energy of the system. There's the free energy of the system. There's the volume of the system and the number of particles in the system. There's G. Okay. What about intensive variables? Anybody give me an example of an intensive variable? Temperature. Yes. Very good. Thank you. Okay. Give me another one. Pressure. Exactly. Pressure. So now let's have a look at what that means in this particular case. So the intensive ones, these ones do not change. If we vary n and v, but keep n over v, the number of particles per unit volume, to be fixed. So that's what we mean by an intensive variable. So what that means is that so G must be an intensive variable. So G must scale with the size of the system. So G must be n times some other function. We know that G depends on T and P. It must be proportional to the first power of n. So it must be proportional to some function of P and T. So we know that that is true. But the other thing that we know is that mu is equal to dg by dn at fixed T and P. And so that means that this function f is actually the chemical potential. And so what we've just derived is that G is equal to N times the chemical potential, which now must just be a function of pressure and temperature. Okay, so that's the basic thermodynamics. Now let's talk about what's called the Gibbs distribution. So I'm calling it the Gibbs distribution, like the Boltzmann distribution. Sometimes it's called the grand canonical distribution. And we're going to derive it the same way that we did before. So it's the same derivation as for the Boltzmann distribution. So I'm going to just scoot through it really quickly because we've done it before. Yes, Jake?
Could you explain why the chemical potential is added? Why instead of
Well, because so we know that G is proportional to N. So therefore it has to be proportional to it has to equal N times a function that doesn't depend on N. So therefore a function that just depends on P and T. But then I also derived from over here, look on the left, we looked at the derivative of G and we saw that, oh, that was bad. Don't want that. What we saw over here was that the coefficient of dn in dg is mu. And because of that, that means that mu has to equal dg by dn at fixed T and P. Okay, so then if I take the derivative of n times f of p and t and say that has to equal mu, then the function f must be the thing that we're calling the chemical potential. Did I answer your question, Jake? What's the thing that you're still puzzled about?
I am puzzled about the final expression.
Okay, if I know that dg by dn is equal to mu, and over here on the left-hand panel, I have dg by dn is f, then what does that mean about f?
Sure.
It's equal to mu. Okay, so I've just told you what the name of that function is. Okay. All right. Chia, you had a question?
Yes.
I just answered your question. Andrew, a quick question.
So the chemical potential is to go on, it just depends on, and so
No.
you add more particles to a system, your chemical potential is not changing.
It just depends on pressure and temperature. Okay. All right. Now let's go through. Let's scoot through this derivation. So let's see what is step one. So step one is I take my joint system. I've now got a reservoir, which we now physically understand. Particles are flying in and out of the system of interest. So the for the joint system, I apply the principle of equal a priori probabilities. And so that means that the probability of finding the system in a quantum state I is the probability that the system S is in quantum state I, and that is then proportional to the number of states of the reservoir when it has ER and NR energy and number of particles. Okay, so that's step one. Step two. In step two, I use the definitions of temperature and chemical potential. Now you have to go back to our isolated system lecture to remind yourself about those. So definition of chemical potential and temperature. So we say that D log gamma of R by D ER at fixed number of particles in the reservoir, that is equal to 1 over KBT, and D log gamma of R by dNR at fixed energy of the reservoir is equal to minus mu over KBT. So those were the definitions that we gave in week one or whenever it was for a system which is an isolated system. And remember what the reservoir property is. The property of the reservoir these quantities stay constant when in contact with our subsystem S, because the reservoir is so much bigger than the subsystem. So that's the reservoir property. So now what I have to do is integrate those two first order partial differential equations. So step 3 is I integrate. And so I've got two integrals, they have to be the same thing. If I integrate log gamma with respect to E, it's going to be something, and then there's going to be a constant of integration which can depend on N. If I integrate the one with N, there's going to be a constant of integration which will depend on E. So I have to put them all together. And so if I integrate, then what I simply get is that gamma R is proportional to E to the ER minus mu NR over kBt. But the total energy is a constant, so ER plus EI is equal to constant, and NR plus NI is equal to a constant. So therefore, so remember, so notice now, comment, definition of state means the number of particles in the state and then the state itself. So basically, for those of you who know what I mean by this, when we have a quantum system with a constant number of particles, the states are in form a Hilbert space. Here, the number of particles change as well. So I have, for any number of particles you have, then I have a Hilbert space of states. Then for the next number of particles, add one, I have another Hilbert space. So this is what's called a Fock space. So it's a tensor product of Hilbert spaces. So therefore, when we say I, that is a state which is a Fock space, not a Hilbert space. And if you don't understand what I'm talking about, don't worry. Okay, so then now the step 4 of our argument is to put it all together. So then it's like we did before. So the probability of being in the state I is now e to the minus ei minus mu ni over kBt, and is over a partition function. I'm going to write that partition function with this letter chi. That's the Greek letter chi, and the grand partition function, as it's called, I is then the sum over states, and now but states including particle number as well as all the other things, ei minus mu ni over kBt, and this result is the famous Gibbs distribution or grand canonical distribution. So let me just wrap up. So we can derive many results by differentiation, just like we did for the Boltzmann distribution. So let me just give you some examples. The expectation value of n is equal to the sum over I ni e to the minus ei minus mu ni over kBt divided by chi, and that then is equal to kBt over chi d chi by d mu, and so therefore is equal to kBt d log of chi by d mu. So that's how I get the expectation value of n. And I would like to suggest in the discussion session that you check this, check your understanding. And there's various other things which I'm not going to rush through now. So we'll just leave it like that. Next time we'll start off. We'll work out the analog of entropy, the grand canonical entropy. It's all exactly the same as it was for the canonical one, and then we will have finished our formal theory. I still haven't told you I've told you now what the grand canonical distribution represents physically. Remember, I told you there's going to be two things that I'm going to tell you which will make sense, make sense. The first thing is, what do all these different distributions mean physically? And so the answer to that is in this picture here on in the bottom of the left-hand panel. That's the picture that you put on your cheat sheet for an exam. It's a picture that if you want to become a statistical mechanic, you engrave it into your contact lenses or something like this. Okay, that's what you're doing when you're doing statistical mechanics, is that picture on the left-hand panel. Okay, the second thing is, I haven't yet told you why computing in the grand canonical distribution is so much easier than computing in any other way, and we will see that either on Wednesday or a week from today. Anyway, we'll finish there. We will go downstairs to our other room and have our discussion session there. I put on Canvas for you some possible exercises for those of you who want to work through them, or you can just work through the homework. One exercise is on second quantization. The other exercise is on using Jacobians to do thermodynamic identities. If anybody wants to do those things, that's the place to do it and learn about those things. If you don't want to, just work on the homework or just ask me and the grader any other questions that you want answered. Okay, so that's it for today. So let me turn off Zoom and I will see you downstairs then in the other room.